of a CFT on a thermal circle, this is similar to that, where you have two possible bulk geometries with the same boundary geometry. And then what you have to do to understand which one actually kind of dominates in the gravity path integral, you just look at which one has a smaller action. Yeah. These are still Euclidean. Okay, so so our goal right now is to write down a Euclidean geometry, and then we're going to end up doing some analytic continuation that I'll explain to actually understand the space-time geometry dual to our state. Okay. Yeah. So the recipe is basically to find the Euclidean solution whose boundary geometry is this. That will be time symmetric. And we'll slice it at time equals 0, and that will tell us the initial data for our Lorentzian evolution. Okay, so that's the recipe. So first we need to decide which one of these to use, and it turns out that for this one will correspond to a black hole, and this one will correspond to not a black hole. So this is like in analogy with Hawking-Page, this is like the high temperature phase, and this is the low temperature phase. So for us, this one will dominate when the tau 0 is small. When we have very high energy states, this is the right picture if that cylinder is very short and fat. And this one will be relevant when tau 0 is larger. Okay, because remember, when tau 0 goes to infinity, we should just get back pure ADS, and that's what we would get. Okay, so this is the picture to focus on. I'll just now assume that our tau 0 parameter is small enough that this is the right picture. So finding the precise geometry here now depends on what parameters we choose for our end-of-the-world brane Lagrangian. Okay, and so depending on the parameters, we're going to get a different solution in detail. What we did was just to take the very simplest kind of example where the only coupling to bulk fields was through the stress energy of the brane, and so we just have one parameter, which is the tension parameter of the end of the world brane. Okay, and then we can find solutions as a function of that tension parameter and this parameter, and sort of investigate their physics. Okay, so to find this dual Lorentzian spacetime, so we have this Euclidean geometry, which is like the exterior of this red hyperboloid and the interior of the cylinder. And now, as promised, that has a symmetry upon time reversal around that tau equals 0 slice. And the shaded gray region is a spatial geometry that forms the initial data for our Lorentzian solution. Okay, so that's the topology, sort of this annulus, where outside here at the boundary, that's the asymptotically ADS part of the space-time, and then when you go in, you actually hit this end-of-the-world brane. Okay. Now I'll actually take this and include the information about what the actual metric on that space is. Okay, and so it turns out that the metric, if I look at the metric, it looks like this. So it looks like, well, there are actually two possibilities. One possibility is that it is the metric of a Schwarzschild black hole outside the horizon, and then past the horizon you get a little bit more geometry, and then it ends on our end-of-the-world brane. Okay, so this is the case when the tension parameter that we introduce for our end-of-the-world brane has one particular sign. Okay. If it has the other sign, then this end-of-the-world brane is on the outside, is up here, and then the space-time just terminates before you would get to what would be the horizon. Okay. So there's these two possibilities. I'm going to be more interested in the one that I've drawn. Because then that's really looks like a black hole geometry, and then there's something specific behind the horizon.
Is that positive or negative?
So it is what we call positive tension. Let me tell you something about CFT interpretation of this parameter. Okay, so actually Tadashi in an early paper on this subject kind of established some connection between that tension parameter and what's called the boundary entropy that is, so there's a quantity that is monotonic under RG flows. And so higher values for this boundary entropy mean that you can flow from that theory to some other theory, but only to lower values of it. So it's something like a measure of the number of degrees of freedom that the boundary of your CFT has. Okay, and so this case corresponds to the case where you have a large boundary entropy. So if that boundary that we introduce has a lot of degrees of freedom, then you get this case. And if it sort of removes degrees of freedom somehow, then you get the case where this end of the world brane is outside the horizon.
In that case, probably unstable, right? Tension times the area is.
In the other case, yeah, it's not even totally. So an interesting question that I'm currently thinking about is what actual values of these parameters are possible in microscopic examples. But the other case does seem a little bit more sick. But.
Does it make sense to ask, like, is the null energy condition obeyed in the brane?
Yeah, I think the energy conditions are not violated in these spacetimes. Yeah, yeah. So it's.
I would have guessed negative tension would violate it.
Yeah,
so then that means positive.
And also tension times the area is.
Well, you guys.
Don't break the energy condition because it will contract in that.
Yeah.
An orange world can have a negative tension. So of course, it will be non-dynamical cases. Yeah. Non-dynamical.
Anyways, yeah. As far as I know, that you don't violate the energy conditions. Okay, right. So I was just saying that the detailed properties of this inner boundary depend on the boundary condition chosen to define the state. And so we could get, say, more of this space-time behind the horizon, apparently, if we chose boundary conditions in the CFT that sort of are associated with having more degrees of freedom. So, yeah.
Is that inner edge still one of these smooth cappings off, like the?
Well, in our, again, I'm taking this bottom-up approach, and so for us, it's just okay. There's a brane there, and I've introduced that in my model by a particular boundary action. Now, I think the very interesting thing would be to just repeat all of this. If you could really do it for using type 2b supergravity and actually put some specific microscopic boundary condition on n equals 4 or something, and then really understand what are the solutions then. But my feeling is that qualitatively this is going to be right, and that the space-time, instead of having that brane, that something will smoothly cap off. So actually, I'll just mention this is very analogous. Okay. So there was this whole story about coming up with CFT duals for